Okay, so a matrix group is a subset of GLNK. It's a subgroup of matrices, and it's going to fit. We're going to think about it fitting inside the general linear matrices over K. Here, K could be the reals, could be the complexes, it could be the quaternions, and there's a natural way to give G a manifold structure. Basically, you just use the identifications we've had, the rho n, the psi n, to convert G to a corresponding group of real matrices, and then that real matrix group, it's either n by n or 2n by 2n or 4n by 4n, and then you can just use the component mappings to give you a coordinate, to get a coordinate chart on G, hence making a G a manifold. Now, if you know what a manifold is, great. If you don't, you can retap for more. But you can follow along here, whether or not you know the technical nuances of manifolds or not. It won't make too much difference here. You can still appreciate what we're doing. But that's one of the reasons that Lie algebras and Lie groups are so much fun to study, is they give you a nice concrete example of where manifolds do something interesting. Now, our definition, a tangent space is always an important thing to understand, and first of all, you could define the tangent space just to be the set of all tangents to curves, like so. I suppose just from basic principles, you might not expect this as a linear space, but in fact it turns out to be such for a Lie group. Now, what's a Lie group? A Lie group is sometimes called a continuous group. Let's see here. I mean, there are certain matrix groups which aren't Lie groups. Discrete groups, for example, groups that just have a couple things in them wouldn't be Lie groups in the way I'm talking about Lie groups here. So we're thinking about a subgroup of matrices which has infinitely many matrices in it. So we can actually make this an interesting construction, right? You have the assignment of lots and lots of different matrices as your time parameter goes between minus epsilon and epsilon, all right? So with this in mind, we make the definition of the Lie algebra to a matrix group. It's the tangent space to the Lie group at the matrix group at the moment, of course, at the identity. And we denote frac G is frac G of G, which is the tangent space identity to G. So once you have that, you can think about, again, the calculus. Here I'm just, again, admitting the calculus is done like this. We always have this as, we can always look at MNK as Euclidean space by making the correspondence to the reals, right? Either this goes to that or this goes to that, etc. Furthermore, what do we mean by that derivative of the curve? I don't want to get buried in the details here. Although I will give you a fair amount of them. So if gamma is a curve of matrices, that means it's a matrix of functions of t. And to differentiate such a thing with respect to t, you just differentiate component-wise, right? D gamma dt gamma prime of t is just that. And you can, so the sum of the derivatives is the derivative, of the, words. The derivative of a sum is the sum of the derivatives in the usual way. Same is true for complex as it is for quaternions, as it is for reals, and likewise for matrices. We're even so fortunate to get a product rule which survives these different notions without qualification. We have the same product rule for quaternions, for reals, for complexes, and for arbitrary matrix multiplications over those. So now I've stated this product rule for square matrices, but I think something also similar is true for multipliable matrices that just have matching, the right row column sizes to multiply. So here it is. The derivative of the product is the sum of the first times derivative of the second plus derivative of the first times derivative of the second. You might write this first and write that second, but addition's commutative, so it's all good. Now, so first of all, for k equals to r, this is the usual product rule for n equals to 1. For k equals to c, you can calculate the product of gamma and beta is this. So the proof is as follows. He proves the product rule for k equals to r for c and for h. He argues that the product rule for ordinary multiplications over k is true, and consequently you can prove the matrix case through a calculation which follows immediately. So that's where we're going here. So here's the product of two complex valued functions of a real variable, and so when you differentiate them, you've got product rule, product rule, product rule, 4 product rules, bop, 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 bop. But of course you can rearrange terms and match that that is in fact just the same as the product of this and that. I mean, in other words, this rearranges to be equal to, it's not hard to see, I'll use red. You can work out that that of course is a fine gamma beta prime plus gamma prime beta, although I really want to write it these terms reversed. But anyway, it's easy to verify that that is in fact these. Just take the derivatives, multiply them out, you can see it works. Of course, this is something I don't know if I prove this in complex analysis actually. I should though. I really should. Anyway, a very similar calculation goes through for the Quaternions, and so that brings us to, oops, a very similar calculation goes through for the Quaternions, because nowhere did we use, when you go through what we did here, we didn't use, nowhere do you use the commutativity of elements, so basically a very similar calculation shows you for Quaternions that holds, and it's important that the order of the elements is maintained. That keeps you out of getting into trouble with the Quaternionic multiplication. So finally, the matrix product used through the usual argument, derivative of the product. Oh, man, this is missing something. Maybe these parentheses. Sorry to be obnoxious about the parentheses, but so the derivative of the product, the ijth element, is the ijth element differentiated. But then this is either a real product, a complex product, or a quaternionic product. The point is, whichever one it is, we have the we have linearity, we have additivity, and we have the product rule for each component product. Which is, then again, this is just a real multiplication, a complex multiplication, or a quaternionic multiplication, all of which satisfy this rule. And then working backwards, we get this matrix sum and product. Nothing too surprising here. In fact, I've worked this out over general associative algebras with without much more trouble. Yeah, that's true. Now what follows is, I think, a little bit less trivial. So here it is. Proposition: if you've got a curve in the general linear group of either real, complex, or quaternionic matrices, and it's a differentiable path, then the mapping T goes to the inverse. All right, this is the inverse in the sense of matrix inversion. That's also a differentiable path, and more than that, the derivative at time 0 is minus the derivative of the original path at time 0. So here's how you prove such a thing. So we have this equation that, and the proof of this is worth looking at, because this kind of shows you how we're going to actually find explicit characterizations of the Lie algebras of all your favorite matrix groups. And by favorite, I just mean the orthogonal ones and the special linear ones. That's about it. But so here we go. The product of gamma of t and gamma inverse of t is I, so I can differentiate that, right? I can differentiate that, and of course I differentiates to 0, has no time dependence, or the time dependence is trivial anyway. Let's see here. So this product rule, but then gamma of 0 is I, and of course gamma inverse of 0 is also I. So plug in time equal to 0, evaluate, and you get that. Simple as that, because this goes to the identity matrix, that goes to minus gamma prime of 0. Here's a picture, for what it's worth, of all that. I should get one of those little thummy things. More and more trouble flipping these pages. So, you know, a picture of what's going on there, something like this. Here's your curve gamma. Gamma prime of 0 goes this way. Gamma inverse prime of 0 goes that way. And the inverse curve is not just the curve reversed. It's something else. I mean, but however that other curve looks like abstractly, the inverse curve has to, when it gets to this identity point, it has to be going in exactly the opposite direction. All right. So again, the inverse curve is not just the reversal of the curve. It's something more interesting in the matrix group. Another proposition from page 70 of TAP, the Lie algebra frac G of a matrix group G is a real subspace. All right, so as promised, it's a real subspace. Now here's the proof. If I have A and B in frac G and lambda are real, there exists curves alpha and beta to G for which alpha of 0 is equal to I, alpha prime of 0 is A, likewise beta prime of 0 is B. And so if you look at the curve sigma, which is the product curve of alpha and beta, pointwise defined product, right? And this is the multiplication of matrices here. Then sigma prime by the product rule is that. So, of course, if you plug in 0, this is the identity, that's the identity, and so you get A plus B, which shows you that A plus B is a tangent to a curve at the identity, which shows you that it's again in the Lie algebra. All right, so this space is closed under addition, and likewise, if you look at the scalar multiplication, you also get that the lambda times alpha has derivative at 0 of lambda A, which makes lambda A in the tangent space at the identity of the group, which makes it in the Lie algebra, and so this frac G is closed under addition and scalar multiplication by reals, and consequently it is a real vector space. I think I'm off the page now. Oh, no, I'm not. So G, frac G, is a linear subspace of MNK as a real vector space. All right. Now, as we've defined it, this doesn't actually have to be a set of real matrices, right? But it does have this real vector space structure. So of course you can trade frac G for a corresponding honest to goodness set of real matrices, or even RL of sufficiently large. I mean, there's all kinds of things you can do if you're willing to work through some maps. But this much we can say: the dimension of G as a manifold is the dimension as a real vector space of its Lie algebra. All right, so the Lie algebra tells you the dimension of the Lie group in particular. I mean, there's a patch in the language of elementary differential geometry. If you take the exponential mapping on the Lie algebra, it will get you some matrices in the Lie group around the identity, and if you restrict it, suitably restrict it, it's even injective. So, but anyway, that's getting ahead a bit. So the tangent space identity to a group is a real subspace of MNK, where K is either C, H, or of course R. Now I'm not sure if it is a complex subspace or if it's a quaternionic subspace. That's not certain. I don't know about that. All right, so actually I'm going to just stop here for a second, get a drink, and start again at proposition 5.6.